In the video classes, we're going to take a look at a reading from Level 1 Quant, Common Probability Distributions. So we've got a few distributions to look at, some more important than others, and I'll let you know that along the way. But first we need a little bit of terminology. When we talk about a probability distribution, it gives the probabilities of all the possible outcomes for a random variable. So you see a bell-shaped curve, that's a normal distribution, probably familiar with that. That's one type of probability distribution. If I'm flipping a coin and I say, well, 50% chance of heads, 50% chance of tails, that's a probability distribution. And a discrete distribution has a finite number of possible outcomes. So our coin flip is either heads or tails, so that's finite. So that would be a discrete distribution. A continuous distribution has an infinite number of possible outcomes. And I've got a couple examples to bring those points home here on the next slide, I think. Yeah, if we talk about the number of days next week that it's going to rain, that's a discrete random variable. There's 8 possible outcomes if you count 0 days of rain. So those are the possible outcomes. That's a discrete random variable. It's got a finite countable number of possible outcomes. Now with a continuous distribution, and to carry on this example, think about the amount of rain that falls, and think about a world in which we can measure it to any degree of precision that we like. Well, that's a continuous random variable, because the probability of any one outcome is 0. It's only over a range that we can define this. But it's a continuous random variable because whatever 2 measures of rainfall we can come up with, there's always room for another one in between. So that's why we say there's an infinite number of possible outcomes. Now let's say, what's the probability of getting 3 inches of rain next week? Well, that may be high. Let's say 0.3 inches of rain next week. But if you go 0.30000 as far as you like, then the probability of hitting that right on the nose is 0. So a probability function gives the probability that a discrete random variable will take on the value x. So this is for a discrete random variable, and we've got an example of one here. Now remember the two what are they? The 2 characteristics of a probability function or a probability. One is it can't be more than 100%. That's certainty. And it can't be less than 0. And the other one, besides being bounded by 1 and 0, all the probabilities, if you take all the possible outcomes and their probabilities and sum them up, it should equal 100%. And that's what we've got here. Our probability of these 5 values that might come up is x over 15. So the probability that 1 will come up is 1/15. You see in the example here, we've got the probability that 3 will come up is 3/15 or 20%. So that's a probability function. It doesn't come up much in the curriculum at level 1, but we can also have a probability density function. That's what we use for a continuous random variable. And we won't have to deal with these because in order to get probabilities on those, you take a range and then integrate across that range. And we don't integrate in level 1 CFA material or any of the other levels for that matter. So a cumulative distribution function is a little bit different than our probability. It's cumulative in the sense that it starts over here at -infinity and gives you all the probability up to a point. And so one way to say that is the probability that a random variable will be less than or equal to a given value. So wherever we put the given value, however much probability is in that distribution between there and -infinity, that's our cumulative distribution function. Now, if we looked at the probability function we had in the previous slide, x over 15, and we said f of 3, well, that's the cumulative distribution function for the value 3. So it's less than or equal to 3. So we want the probability that 1 can occur, 2 can occur, and 3 can occur. So we have 1/15 plus 2/15 plus 3/15. We get 6/15, which is 40%. So whereas we did the probability of 3 was 3/15 or 20%, the cumulative probability function for 3 and this discrete probability distribution is 40%. Now, if we're talking about a continuous distribution, there's one thing about this cumulative distribution function and the way we can use it here. And we'll illustrate this in an example. Say we're looking at the percentage ROE for a firm, and that's X, that's our random variable. And it's defined over the range minus 20 to plus 30, so clearly we've got it in percent. And then we say, well, the CDF, the cumulative distribution function, capital F of X, is X plus 20 over 50. And here we're asked, what's the probability that the ROE will be positive and less than or equal to 15%? So if we've got some distribution, and I'm not saying this is the distribution we have, but we can draw one like this and say, well, here is 0, and here is 15. So what we're after is that probability right there in the problem. And so our solution technique is going to be to use this cumulative distribution function and get the probability, the cumulative probability all the way up to 15. And then we're going to get the cumulative probability all the way up to 0. And so our answer is going to be this probability here, cumulative probability, minus this cumulative probability has got to be this difference between them here. So let me clear this off and show you what we do with the numbers and the function that we've got here. Okay, so we want the probability that 0 is less than equal to X is less than 15. We didn't put less than or equal to here. We could have, but remember, with a continuous distribution, the probability of any single number is 0. So the less than or equal to becomes less important than it was for our discrete distribution example. So we want to take f of 15, that cumulative distribution function for 15, minus the cumulative distribution function for 0. So first we plug in 15 to the formula values and get 35 over 50, or 70%. And then we plug in 0 and get 20 over 50, or 40%. So 40% of our outcomes are going to be negative, less than or equal to 0. And then just take that difference and find out that in that range that I drew, such that I drew, just laughing at my own artwork here, is 30%. So that's one way we can use a cumulative distribution function for a continuous distribution. So now let's define another type of distribution. This one's called a discrete uniform. It's very easy to remember. It's a discrete probability distribution, so there's a finite number of outcomes, and each one is equally likely. So if we have 20 possible outcomes for a discrete uniform distribution, the probability of any one of them occurring is 1/20th or 5%. So if we take an example and say, well, the probability of X is 0.2 for X equals 1, 2, 3, 4, 5. Well, that works out because 20% times 5 is 100%. And now we can easily calculate our cumulative distribution, f of 3. Remember, that's less than or equal to 3 with a discrete probability distribution. So we've got the probabilities of, get my pen over here, my magic pen, 1, 2, and 3. So that's just 3/5. 3 out of 5, and clearly 60%, or 3 times the probability of each one. So the uniform just tells you it's flat. The probability of each one is the same. They're all equal. Okay, let's get to a little more complex distribution here, and that's our binomial distribution. We're going to start by defining a binomial random variable, and the type of problems where you want to use this is when there's only 2 possible outcomes. That's the bi in binomial, 2 possible outcomes. So up or down, rain or shine, okay, above 5%, less than or equal to 5%. Any problems that are defined like that might be ones where you're going to apply a binomial distribution or calculate a binomial random variable. So the idea of this formula here, which isn't as daunting as it looks, is that we're going to have a trial and we're going to see how many successes we get. So maybe the easiest way to think about this is a barrel full of balls where some are black and some are white. And we can define success either way as either choosing a black one or choosing a white one. And then what we're going to calculate is the probability of exactly X successes in N draws. So we're going to draw, without looking, we're going to draw balls out of the barrel. And if we define success as getting a black one, and we say, well, what's the probability of getting 3 black ones in 5 tries? That's what this formula is. So it's exactly 3. Remember, it's not 4, it's not 2. It's exactly 3 in 5 tries. Well, this is the formula for it. And what we have here, our P here, this right here, that's the probability of success. Okay, probability of success. And 1 minus that, that's got to be the probability of failure as we define it, and that would be getting a white one. So what we need is to know what percentage of the balls in the barrel are black. So if there are 60% of the balls in the barrel are black, then this probability of success, the probability of choosing a black one with a random draw, is going to be 0.6. This probability of failure, that is drawing a white ball, is going to be 40%. And then we have this N choose R, or N choose X here on your calculator. It's N choose R. Now this function is on the Business Analyst 2 Plus, the TI calculator. It's not on the HP calculator. So you might want to take one of those BA calculators to the exam with you. And that way you don't have to memorize this formula with factorials and everything in it. So we're basically answering the question here, how many ways are there to choose 3 black ones in 5 tries? That's what that tells us. So if we're talking about 5 tries and 3 black ones, well, one way to do that is black, 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 white, white. And another simple one here is black, black, white, black, white, white. So that's what this term right here does. How many ways are there to order these? How many did I get too many here? Black, black, white, black. Yeah, I got too many here. We'll take that one off. That's not going to work. Okay. So we've got 2 different ways to get 3, and this tells us how many ways there are to get 3 black ones in 5 draws. And it, well, we could run it on the calculator, but we'll see a numerical example in a minute. But what I wanted to highlight here is, well, what's the probability of this series of draws right here? Well, they're all independent, so the probability of getting that first black one is 0.6, and then 0.6, and then 0.6, and then 0.4, oops, make a better 4, and then 0.4. So those are our probabilities, and we can just, I'll take this one away here now, and so we can just multiply those together and come up with the probability of getting this string. So the only mental leap you have to make here is to say, you know what, the probability of this string is the same thing. Because now we've got 0.6, 0.6, 0.4, 0.6, 0.4. And so the probabilities of getting any of these strings I could name is 0.6 cubed times 0.4 squared. And that's exactly what's in the formula right here. Okay? So this is the probability of success to 3, the number of successes we're looking for, and this is the number of failures, 2, actually, 5 minus 3, because we've got 5 draws, and this is the probability of failure. So if we listed all those out, they'd all have the same probability, and oh, guess what? There's 15 ways we can do that, so we multiply that probability times 15. So that's what's going on with this formula, and hopefully that'll make it a little less daunting, a little bit easier to remember and work with. So Now let's use that and say, well, what's the probability of drawing exactly 2 white marbles from a bowl of black and white marbles in 6 tries if the probability of selecting white is 0.4 each time? Well, let's see if we can do that without the formula. We say, what is the probability of drawing 2, and the probability of selecting white is 0.4. So our probability of success is 0.4, and we need 2 successes. So there you go, 0.4 times 0.4. Well, if we're going to draw 6 times, then we've got 0.6, 0.6, 0.6, and if I've got room here, I'll put in another 0.6. So there's our 4 failures and 2 successes. So that's our probability. This is our probability of success to the number of successes times probability of failure to the n minus x number of failures. And then the only thing we need left is to say, well, what's that number? How many ways are there to choose 2 white ones in a series of 6 draws? And that's going to be this n, which here is 6 for us, choose 2. And so if we multiply all that together, that's the binomial formula. So now let's look at the numbers on this thing. We know that successes are 2, probability of success is 0.4, and that our number of draws is 6. We plug it into this formula right here, which we didn't really need because we understood where it came from. And so we put our 0.6 here, and it turns out there's 15 ways to get 2 white ones in a series of exactly 2 white draws in a series of 6 draws, where the probability of success is 60%. Excuse me, 40% here, probability of failure 60% in this example. So now we're going to look at a binomial tree, and I'm going to relate that binomial formula back to what we've got going in this tree. Now this tree we don't even use at level 1, at least not in the current curriculum. But it's used at level 2, and binomial models are used to price several things. They can be used to price options. They can be used to price bonds with embedded options in them. And a little later on, in level 2, they come up with an interest rate tree as well. But for this one, we need to know the probability of an up move and the probability of a down move. Well, since those have to equal 1, knowing one of them is enough. So what's the probability? Because our binomial outcomes here are either up or down. That's our 2 outcomes. And we need to know, well, what's the probability of an up move? And we need to know, well, if there's an up move, how far does it move? Well, that's the up factor. And that's a factor greater than 1. And we use this often for asset prices. In the example, we're going to start with a stock price of 20 and say the probability of an up move is 60. And our up factor is 1.12. Now, our excuse me, our down factor is just going to be the reciprocal of that, 1 over 1.12. And one thing that does is if we have an up move, multiply by 1.12, and then we have a down move, divide by 1.12, we're right back where we started. So that's why we use the up and down factors that way. So if we know the up factor, we can calculate the down factor. If we know the up probability, we can calculate the down probability, or vice versa. So let's take a look at our tree here. We've got a starting stock price of 20. Probability of an up move is 60. The size of our up move, or our up move factor, excuse me, is 1.112. And so we've got 3 possible outcomes. Okay? We've got up, up. And what's the probability of 2 up moves and 2 draws? Well, that's actually our binomial probability. It's very simple here because we're just talking about a 2-period binomial model, but the probability of 2 up moves is just 0.6 times 0.6, so that's 36%. The probability of 2 down moves is clearly 40% times 40%, okay? dn for down. And so that gives us a 16% down there. Now the probability of a down and then an up is 0.4 times 0.6, that's 24%. But remember, there's 2 ways to get there. a down move followed by an up move, or an up move followed by a down move, both get us there. So our 0.4 times 0.6, our 24%, we need to double that. And that is also an example of the binomial formula. That's actually the probability of getting exactly one up move in 2 trials. It's also the probability of getting one down move in 2 trials. So you might want to fool with that formula and convince yourself of that. So to draw this binomial tree, then we just need to put some prices in, because an up move takes us up 12% and another up move takes us up 12% again. Or we can divide by that 1.12 twice if we have 2 down moves, and the stock price goes to $15.94. And this one in the middle, well, as I said before, an up move followed by a down move gets you right back where you started. So there's our 3 possible outcomes and their probabilities, assuming that this stock is following a binomial model. Well, you're thinking to yourself, how likely is that you could do it like this? Well, the thing with a binomial tree is we can add more and more and more nodes or time periods, moves up or down. And as we shorten those periods and increase the frequency of these up and down moves, of course we scale back the percentages, but it really gets close to a normal distribution as these periods between up moves and down moves get smaller and smaller and smaller. Of course, then instead of 3 possible outcomes, you have 3,000, and so that models it a little bit more closely, and certainly you'd need the binomial formula to type into Excel at that point. You couldn't just multiply these out in your head like we did here. So make sure for a binomial tree, if you're given the probability of an up move and the size of an up move and the beginning price, that you can calculate all the probabilities out here from that information, plus the prices at every node, just from those 3 pieces of information. And if you can do that, you're in good shape. Okay, what's tracking error? This is just a definition that kind of falls at us out of nowhere right in the middle of quant. Tracking error is the total return on the portfolio minus the total return on the benchmark portfolio or the index. So if I'm managing a portfolio and the idea of the portfolio is to match the returns on the S&P 500, if that's my mandate, then the tracking error is how far I missed that. So in this example, if we had a stock portfolio with a return of 4% and we were supposed to be tracking the S&P 500, running like an index fund, tracking an index fund, our tracking error here is minus 3%. Okay, we had the discrete uniform distribution. Now we've got a continuous uniform distribution. And that one's not too bad either, because let me draw something. I know my drawing is not wonderful, but it may help. Think of this box that we draw as 100%. And we've got a variable that's defined, a random variable, 2 to 10. Okay? So 2 to 10, that's 8 wide. All right? So each one of these is 1/8 of the probability. And then I can draw one on this end between 9 and 10 and say that's 1/8 as well. So that's what we mean by a continuous uniform distribution. Now remember, with a continuous distribution, I can't say anything about that. Well, I can. I guess I can say the probability of hitting 3 right on the nose is 0. But we can talk about the intervals. What is the probability of being between 2 and 3? Well, it's 1/8. It's 0.125. It's 12.5%. And if we say, well, what's the probability of being between 2 and 7? Well, 3, 4, 5, 6. So how wide are we? 2 to 7. We're 5 wide out of 8. So that probability there, that whole thing, including this piece down here, so this whole thing is going to be 5/8. And it's just that straightforward. So let me clear this up. and show you the numerical examples here. The probability of x is less than 2, 0. It's outside the range, outside the range. What's the probability between 3 and 5? Well, that's 2 wide, and the whole range is 8 wide. So we've got 2 over 8, and that's 25%. So that's a continuous uniform distribution. Now let's get to a distribution we're going to use quite a bit more than we're going to use those, and that's the normal distribution. Normal distribution, that's your typical bell curve that they used to show you in grade school to show you were above the mean or below the mean or at the mean or whatever. So it's completely described by its mean and variance. And when we talk about the characteristics of a distribution, the first thing, the first moment, as they call it in statistics, is the mean. And that's where is it centered? Where's the center of this distribution? And what's its variance? How spread out is it around that mean? Now, in terms of its symmetry, okay, that is, well, how symmetric it is symmetric. It's a symmetric distribution. If you folded the distribution in half, it would just meet up and match up. So we say its skewness is 0. It's neither positively nor negatively skewed. Kurtosis is a shape measure. It measures the peakedness of a distribution and the fatness of the tails. And for the normal distribution, that kurtosis is 3. So when we say that the normal distribution is completely described by its mean and variance, because it's a normal distribution, we already know its skew is 0. It's a symmetric distribution. And we already know its shape in terms of peakedness and how rapidly its tails, the probability in the tails, gets smaller and smaller. Now, one property of normally distributed random variables is that a linear combination of normally distributed random variables is also normally distributed. And the probabilities decrease further and further from the mean, but in theory, in statistics, they go on and on forever. They just get thinner and thinner and thinner. There is some probability of outcomes way out here. It's just really, really, really small. And sometimes we talk about a multivariate normal distribution. That generates 2 or more. I guess with 2 it's a bivariate normal distribution, but multivariate covers 2 or more than one random variable. And so if we have the mean and the variance and the correlation between these two, that's what we mean by a multivariate distribution. It's actually generating 2 random variables that have the mean and the variance and the correlation between them that's specified by that function. So now we're going to talk about a confidence interval for a normal distribution. And this is in terms of standard deviations. And you can see we've got this bell curve here, or something close enough to it to work with. And here's the mean. Here's the expected outcome, the expected value of x. So that's the mean right there in the middle. And then we've got some information on how spread out it is. But here we're not dealing with that. Okay? We're dealing with just the number of standard deviations from the mean. So we're not dealing with the actual random variable outcome itself. We're dealing with, well, how far is that outcome in standard deviations from the mean? And we say for a normal distribution, 68% of all of the possible outcomes are right here within plus or minus 1 standard deviation either side of the mean. And if we expand it to 2 on either side, we're clearly capturing a lot more of the possible outcomes, and that's about 95%. So what would that put in this tail here and this tail here? You're exactly right. You'd put 2.5%. That puts 2.5% in each tail, and percent sign, and 95 here in the middle. Now, we'll have occasion to memorize a couple numbers about this right here. For now, you should memorize this one. 1 standard deviation either side, about 68%. And what's that put in each tail? Right. 1 minus that is 32%, but you need to divide that by 2. So what's in the tails outside 1 standard deviation below the mean and above 1 standard deviation above the mean? 16% in each tail. So now here's some of those numbers I said you need to memorize. When we want a 90% confidence interval, we can get that with a normal distribution by taking an interval that's 1.65 standard deviations either side of the mean. If we want 95%, we've got to widen that to 1.96 standard deviations either side of the mean. And if we want to capture 99% of that distribution, that is, leave 0.5% in each tail, then our interval is from minus 2.58 standard deviations below the mean to the mean plus 2.5 standard deviations. So whatever that comes out to in numbers. So take a look at this example. The mean annual return is normally distributed on a portfolio over many years is 11%. And we know the standard deviation of returns is 8%. Calculate a 95% confidence interval on next year's return. Well, when we want a 95%, we've got to go 1.96 standard deviations. We know the standard deviation is 0.8, and we know the mean is 11. So let's start with 11 and add and subtract 1.96 standard deviations, and we get an interval from minus 4.7% to 26.7%. So for this portfolio, based on these numbers, we'd say there's a 95% probability that next year the return will be between minus 4.7% and plus 26.7%. So that's how we can establish a confidence interval. Given the mean, the standard deviation of observations around the mean, and the percentage confidence interval that we want. So what's a standard normal distribution? Well, a standard normal distribution, that's the one that's going to be in the back of the book where you can look up probabilities. That's based on a standard normal. And what's standard about it is we standardize the standard deviation to 1. And we put the mean on 0. And we do this so that we can do tests on a number of different normal distributions with different standard deviations, different means, different units of measure. And so what we'll do is we'll calculate the z-value, but don't get too intimidated by this particular calculation here, is because all we're doing is, here's our observation, right? Our observation is x. And we're just going to take x and say, how many standard deviations from the mean is it? And that's called standardizing it, because how many standard deviations from the mean is it is the same question as where would it lie on a standard normal distribution, because each standard deviation is 1. So 1.96 standard deviations above 0 is 1.96. Becomes a lot easier to work with. We only have to put one table in the back of the book instead of a lot of them. So our z statistic is just how far from the mean in standard deviation units are we with each observation. So now let's calculate some probabilities using the standard normal. The earnings per share for a large group of firms are normally distributed with a mean of $4 a share and a standard deviation of $1.50. Find the probability that a randomly selected firm's earnings are less than $3.70. Well, we've got the tools to do this now. May have to look it up on the table, but I've got an excerpt coming up. So how are we going to figure this out? Well, one thing, we can do that standardized and say, well, 370, what is that? Well, that's 0.2 standard deviations below the mean. Excuse me. And so we want to find out, what's the question? The probability the randomly selected firm's earnings are less than that. So if we're drawing a picture here, here's our mean. And again, sorry about the artwork, but that's it for me. Okay, so there's our mean 4, And we've got our number 3.7, let's say, 370, and we're asked to find the probability out here. Well, there's a couple ways we can do that. We can look that up on a negative z table, and if we looked up the value on the negative z table for minus 0.2, we'd find out the probability of being less than that. Because remember, what's that table we're looking at? It's a cumulative distribution function. So the value for minus 0.2 is all the probability from negative infinity up to minus 0.2. And then we're also going to show that with a symmetric distribution, if I go out here, let's see, 30 cents, $4.30, that is 0.2 standard deviations above the mean. If I looked that up on the table, I would get all of this area here, right, from the cumulative distribution table. And if I took 1 minus that, I'd find this tail, which is the same thing I'd find on the negative tail, because it's symmetric. So the probability of being less than minus 0.2 standard deviations below the mean, or getting a value more than plus 0.2 standard deviations above the mean, are exactly the same thing. And that's what we'll show in the numbers for the rest of the example. So we're 0.2 standard deviations below the mean. So now we can go to a z-table. This is a positive z-table. I don't know which you might be given if you have to solve a problem like this. But now we go to 2.0, where they cross, and we come up with 57.93. That's the probability of getting a value below, less than or equal to 0.2 standard deviations above the mean. So what do we have to do with that? Well, we just have to take 1 minus that, and we can come up with 4207. Now, had you looked it up on a negative z-value table, then 2 and 0 would have had that in the box right there. And how do you know which is which? Well, 50% is the dividing line, right? That's 0 standard deviations from the mean. So for negative, we should be less than 50%. For positive, we should be more than 50%. So that should help you keep that straight. So here's that picture I tried to draw before, except done better, okay? If we had a negative z-table, we'd look up minus 0.2 and find out that's the probability, less than or equal to that. Or we could look it up on a positive z-table and get that value we found, which was 57.93, and take 1 minus, I think it was 57.93. Let's pretend it is for our purposes here, okay, 0.5793. And that's also going to give you this value right here. So that's how we can use these probabilities from the tables. Now let's talk about some applications in finance. One is shortfall risk. Shortfall risk is a probability. It's the probability that a portfolio return or value, we can do it in return percent or we can do it in dollars or euros or whatever, will be below a target return or value. And what do we use this for? Well, we can compare portfolios. When one portfolio has a higher expected return but more risk, how do we compare it to a portfolio that has lower expected return but also lower risk, which is a good thing? Well, we can look at their shortfall risk relative to a particular return value, let's say. So we could say, well, 0. We're really concerned about negative returns. We want to choose the portfolio with the smallest probability of giving returns below 0, of giving negative returns over the next period. Well, that would be choosing the portfolio that minimizes the shortfall risk given a threshold or a target of 0% return. Now, a little older version of this is Roy's safety first ratio, but it's based on the same idea. Roy's safety first ratio, we take the expected return, so we take the mean return here. And this threshold return has got to be less than the mean, or at least it always is in this application. So here's our threshold or our target return here. And then here's our standard deviations. So what are we measuring? We're measuring, here's our mean, okay, and, excuse me, here's our mean and here's our target return. It's somewhere below the mean. And we want to choose the portfolio that has the least out in this tail. And that's going to happen when? When this threshold is the most standard deviations below the mean. The more standard deviations below the mean we are, the less probability out in that negative tail. Now you might remember the Sharpe ratio. If you look at this and we say our threshold rate of return is the risk-free rate of return, then the safety first ratio is the same as the Sharpe ratio. And again, remember, we like a low shortfall risk, but we like high Sharpe ratios, and we like high safety first ratios because that safety first ratio is expressed as a positive number. It's the number of standard deviations below the mean this benchmark or threshold or target return is, expressed as a positive number. So we like a high safety first ratio, we like a high Sharpe ratio, but we like low shortfall risk because that's the probability of returns below a particular value. Now, just to highlight that, let's take a look at an example. We've got two portfolios here, A and B, and A has an expected return that's lower than B's, but it also has less risk. And so how are we going to decide between them? Well, we had one measure earlier in quant. You had the coefficient of variation, and that's one way to do it. But here we'll do it with a safety first ratio. And we're going to put our target return as 5%. So using 5% and choosing the portfolio with the higher safety first ratio means we've chosen the portfolio that has a lower probability of returns below 5%. Well, it turns out the safety first ratio for portfolio A is 0.83, and for B it's 0.52, and we like the higher one. And I just put this on to bring this full circle to illustrate this point. This n, that's the cumulative normal distribution function. That's what we were reading off the table. And the probability, the cumulative probability up to negative safety first ratio, so the probability of being more than 0.83 standard deviations below the expected or mean return of 15% is 20%. So the probability of being less, of getting a return below 5% is 20% with portfolio A. With portfolio B, that 5% mark is less standard deviations below the mean. It's only 0.52. That leaves more in the tail. The probability of getting returns less than 5% with portfolio B is 30%. Or 30.15 if we're going to be real precise about it. Okay, next we want to take a look at a log normal distribution. This is fairly straightforward. There's only one reason you need to know it. We use it to model asset prices sometimes, or price relatives. Price relatives is what we multiply a price by. So if something goes up 5%, the price relative is 1.05. We multiply by that. Okay? But we can't use a normal distribution for asset prices or returns because returns are bounded. They can't be more than minus 100%, at least if we're talking about a fully paid for asset without derivatives or leverage or something like that. And especially if we talk about stock prices. Stock prices don't go below zero. They do go to zero, unfortunately, but they never go below zero. They never send you a bill for owning a stock. They can tell you your stock is worthless, but you can't get a bill for their mismanagement after the fact. So they're bounded by zero. So why do we call it a log normal? Well, if X is normally distributed, right, bell curve, positive, negative, infinite tails, then this mathematical e to the x is distributed log normally. And here's what it looks like right here. It starts from 0 and then goes up and then tails out. So the reason we like to use that log normal distribution, because it's bounded by zeros and we can model asset prices as following a log normal distribution. And how do you get the values? You just pick x from a normal distribution and take e to the x and just keep doing that, and that will give you a log normally distributed random variable. Okay, continuous compounding, another one of our quantitative tricks here. Remember back when we started talking about time value of money, we said, well, the more frequent the compounding periods, the greater the effective rate of return, right? For a given annual stated rate of 8%, why the effective rate was higher with quarterly compounding and higher than that with monthly compounding. We could talk about weekly compounding. We could talk about daily compounding. Well, the limit of that whole process, as these compounding periods get shorter and shorter and shorter, is continuous compounding. So we're given an annual stated rate, but then we want to know what's the effective rate with continuous compounding. So that's what we're up to here. So the equivalent annual yield with continuous compounding is e to the interest rate minus 1. So that's our effective, I guess I said equivalent. I think effective annual yield or effective annual rate is what we're after here. So looking at that example, for a 1-year holding period, our return is stated at 8%. But with continuous compounding, what's our effective annual rate or effective annual yield? Oh, I've told you backwards. I'm sorry, we're starting with a 1-year holding period return of 8%. So the question is, what is the stated rate that with continuous compounding would result in an effective annual yield of 8%. So I think we'll do it the other way next. But this time, we're given the effective rate. So if you look here, if we take the log of 1 plus that holding period return, we're going to get the continuously compounded rate. So that's as easy as 1 plus 8%. Take the natural log of that with your calculator, and we find out that with a 7.7% stated annual rate, if we took the compounding period down as far as it would go and limit to continuous compounding, our effective annual yield would be 7.7%. And also, notice that if we started with a value of $100 and we ended the 1-year period with $108, we can just go right there and put end, if I can write end over beginning value, take the natural log of that, and come up with the stated annual rate, assuming continuous compounding would turn $100 into $108 in 1 year. So let's go the other way now. You're given a stated annual rate of 7.7%. What is the effective annual yield with that rate and continuous compounding? So we take e to the 0.77 minus 1, and that gets us to 8%. So that logarithm and that e are inverse functions of each other. They undo each other, if you will. And one of the nice things about continuous compounding with this rate, say I said, well, what's the 2-year effective annual holding period yield? Well, I can just take e to the 2 times 0.077. So I just double that exponent, and that gives me the effective 2-year. And so in that way, it's a little bit easier to work with in doing compounding problems than trying to compound for 2 periods with a discrete annual rate. So let's look at a couple more problems here. Make sure you get this down because it's not difficult, and we want you to be able to do it if it comes up on the exam. If the continuously compounded stated rate is 8%, what is the effective holding period yield or return for 1.5 years? Well, now we can use that trick that I just talked about there. Okay, we can take 1.5 years at 8%, that's 0.12, put that in the exponent. work our magic, e to that exponent minus 1, and find out that the holding period return, so this is not an annual rate, this is a 18-month or year-and-a-half rate, 8% stated rate, continuous compounding, how much effective growth in 1.5 years? 12.75%. And put another way, just so you're familiar with all the different ways to use this, how much will $1,200 grow to in 1.5 years? It's dead easy. Take the 1,200 and we multiply it by our factor here, 1.5 years, 8% growth, e to that power, and we get 1353. And that should be an increase of 12.3%, just as we found up here over the 18-month period. So that's continuous compounding. Last two things I want to discuss with you from this reading are Monte Carlo simulation and historical simulation. Now, simulation can be used to estimate a distribution of derivatives prices or net present values. Okay? So say we've got a fairly exotic derivative, or we've got a project whose outcome depends on the amount of sales, the price of the resources, the price of the output good, what interest rate turns up in the future, all these various things. We're trying to value this. Well, one way, and this came up with computers, and when we got to with computers where we could do repeated calculations very quickly, this became a powerful tool. And so what we're going to do is for each of these important variables in determining the value of the option or the value of a project, its NPV, we're going to specify the distribution of each random variable. So we could have a distribution for interest rates. We could have a distribution for underlying stock prices. Remember, we'd want that to be log normal, or to use price relatives based on that log normal distribution. So we specify all these distributions, right? Interest rates can't go negative either. So we specify all these distributions, and then the computer grabs one value for each of our important variables from the distributions that we've described for them, crunches them all together, and say comes out with a value for the option. And then it does it again, repeating that, drawing from all these other distributions for asset prices, interest rates, stock prices, whatever it might be, and keeps calculating values for this exotic option. Okay. And we repeat this thousands of times. Well, what do we have then? Well, then we have thousands of values for this option, depending on outcomes from all these different important variables. And we can look and we can calculate, well, what's the average? What's the mean of those 10,000 random values that we came up with? And that should be the expected value of the option. And we can look at the variance of all those values and find out the variance or the standard deviation of that option price around its mean. So Monte Carlo simulation has to do with this repetition of computer where we specify the distributions. Now, compare that with a little easier method and maybe older method, and that's historical simulation. Here, we're not going to simulate these. We're going to go back in time and say, here's some values for interest rates, asset values, this and that, over the last 5 years. We've got weekly data for 5 years. Okay? So now, instead of drawing those variable values from distributions that we have described, what type of distribution, what's the mean, what's the variance, what's the skew, whatever it is, we're going to draw historical values. So we don't have to estimate the distribution of the risk factors or specify anything about those distributions. We're just assuming however they were distributed in the past, that's the type of distribution we're facing. The disadvantage of that is sometimes the future just doesn't look like the past. And when you get into uncharted territories, or you get outliers, or you've looked at a historical range for your simulation in which something was fairly calm, like an exchange rate was very steady for 20 years, and then if that exchange rate changes all of a sudden, there you go. Big surprise. So that's the drawback of historical simulation. So anyway, that wraps up this particular topic review in our video classes. So Maybe I'll see you in another one.